Welcome back, everyone. The race to perfect solid-state batteries has moved beyond simply improving performance. The newest goal is to make these systems fully recyclable, so that the metals and electrolytes can be reclaimed and reused without waste. This shift reflects the realization that energy storage must be efficient not only during operation, but across its entire life cycle. Researchers are now developing methods to disassemble and regenerate solid electrolytes, retrieve valuable lithium or sodium, and reconstruct new cells from recovered materials. The process is beginning to resemble industrial recycling lines for metals rather than disposable chemistry. Please subscribe now. Solid-state batteries differ from traditional lithium-ion cells because they replace flammable liquid electrolytes with solid layers. These solid layers can be made from ceramics, polymers, or sulfides depending on design. The advantage is safety, stability, and greater energy density, but early prototypes faced challenges when cells degraded after repeated cycling. Until recently, those failures made recycling unappealing since broken solid layers were hard to separate. Now, researchers at Toyota and the University of Oxford have found ways to dissolve and reform these layers through controlled chemical baths that preserve structure while releasing trapped metals. The heart of closed-loop energy storage is the ability to reclaim materials without losing purity. In a standard lithium-ion plant, black mass from shredded batteries requires high-temperature smelting to separate cobalt and nickel. Solid-state systems offer an opportunity to skip that step because their simpler construction avoids heavy casings and complex binders. At ETH Zurich, engineers have shown that mechanical separation and ultrasonic vibration can free solid electrolytes like lithium phosphorus oxynitride while leaving cathode materials intact. Each recovered component can then be filtered, dried, and reassembled into new cells that match the performance of those made from virgin materials. Recycling efforts are already influencing how manufacturers design next-generation batteries. The European Commission has issued new requirements that mandate traceability for all critical metals used in electric vehicles. To meet these goals, companies are turning to modular designs where electrodes can be detached as single sheets. Samsung Advanced Institute of Technology is experimenting with flexible solid electrolytes that peel away cleanly from the anode and cathode surfaces when exposed to mild solvents. This kind of separation avoids contamination and allows lithium metal foils to be reused directly rather than melted down. The chemical principles behind recycling solid electrolytes are pretty straightforward, but they do require precise control. Many of these solid layers are made up of crystalline structures that can break down if they're exposed to water. Instead of using water, researchers have started turning to anhydrous alcohol solutions, combined with mild acids, to dissolve surface films and release those embedded ions. The whole process can take several hours and needs to be done under carefully regulated temperatures. After filtration, the resulting powder is heated up in a vacuum furnace, which helps restore its crystal lattice. At MIT, experiments have shown that these reformed sulfide electrolytes can reach almost the same conductivity as brand new material, which proves that recovery doesn't always mean you have to compromise. Companies that are aiming for commercial recycling lines have also started using automation. Robotic arms are now able to disassemble battery packs, using infrared mapping to locate welds and cuts. Each component gets tagged with a digital identifier, which records its composition and usage history. When the battery reaches the end of its life, all this data helps guide the recycling robots so they process it the right way. Rolls-Royce Power Systems and Hitachi Energy, for example, are working together on pilot plants that combine this kind of digital twin tracking with real-time process control. The goal here is to create a unified line that can recover more than 90% of the active material, all while keeping energy costs to a minimum. A major obstacle still remains because of the diversity of solid electrolytes out there. Some rely on oxides like garnet, others on sulfides, and each type needs different recovery conditions. Moving from the lab to the factory means scaling these processes up to handle tons of material, all while still maintaining purity. Engineers at the Fraunhofer Institute in Germany have come up with a modular recovery platform that can automatically adjust solvent mixtures based on spectral readings of the waste material. Their pilot system uses sensors to identify the type of electrolyte and then selects the right extraction bath. This approach could make recycling universal across different solid-state chemistries, and it wouldn't require retooling entire plants. The closed-loop model extends beyond material recovery to system design. When a battery is built with end-of-life separation in mind, assembly methods change. Instead of permanent welds, removable clamps or laser bonds allow easier access to internal components. Panasonic has filed patents for pouch cells that unfold like layered sheets, exposing each element sequentially. Once unfolded, the cells can be fed into automated lines that remove electrolytes, clean electrodes, and restack them into new casings. This design thinking is turning recycling from an afterthought into a core feature of battery engineering. Economic viability is as critical as chemistry. Recycled solid-state materials must cost less than new ones or offer performance advantages to justify industrial use. According to data published in Science Advances, reprocessing of sulfide electrolytes could reduce material costs by as much as 40% once facilities scale beyond 100 megawatt-hours per year. Analysts expect cost parity between recycled and virgin materials around 2026 if large manufacturers continue current expansion rates. Governments are helping by funding demonstration plants that prove circular manufacturing can meet national energy storage needs without increasing raw material demand. Environmental benefits are equally significant. Traditional lithium-ion recycling consumes large amounts of acid. Solid-state recycling uses lower temperature processes and closed solvent loops that minimize waste. For example, a British startup called Iron Cycle has developed a recovery method that operates entirely under 200 degrees Celsius, capturing nearly all solvent vapors for reuse. Their system runs on electricity from local solar arrays, showing that even recycling infrastructure can follow sustainable principles. Reduced environmental impact strengthens the business case by lowering regulatory costs and public resistance to battery manufacturing. Beyond economics and ecology lies performance. When recycled materials are reassembled into new cells, they often exhibit improved consistency due to refined control during reprocessing. This consistency enhances overall lifespan and cycle stability. Researchers at Stanford University have reported that cells built from recycled solid electrolytes maintain 95% capacity after 500 cycles, compared to 88% for first-generation cells. The repeated melting and reforming process appears to eliminate structural defects that would otherwise form during initial manufacturing. Each recycling round effectively reanneals the crystal lattice and extends service life. The development of closed-loop solid-state systems will also transform supply chains. As more nations establish domestic recycling plants, dependence on imported lithium and nickel will decrease. Japan and South Korea are already forming joint ventures to secure self-sufficient production lines for electric vehicles. North American firms are investing heavily in localized recovery to stabilize supply during geopolitical disruptions. Over the next 4 years, a network of regional recycling hubs may replace today's global shipping model. This shift shortens logistics, reduces storage costs, and strengthens energy independence. A less visible but crucial challenge involves quality control. Recycled powders can contain trace impurities that interfere with ion conduction. To address this, companies use advanced spectroscopy and machine learning algorithms to detect and correct deviations during synthesis. Data from each batch is compared to reference spectra stored in central databases. If conductivity falls below target thresholds, process parameters are adjusted automatically. At Lawrence Berkeley National Laboratory, engineers are applying reinforcement learning to optimize these adjustments in real time. The system learns how to maintain uniform crystal size and orientation for maximum performance. Scaling these technologies requires collaboration across industries. Mining companies are partnering with battery makers to align extraction volumes with recycling outputs. Automotive manufacturers are redesigning pack enclosures to make removal simpler. Utility operators are investing in large stationary solid-state arrays that can be maintained and recycled on-site. These efforts form the basis of a true closed-loop ecosystem where nothing is wasted. Over time, the value of recycled material will rival that of raw extraction, creating a stable and predictable supply cycle for decades to come. While optimism is high, technical limits remain. Some solid electrolytes lose conductivity after multiple reprocessing cycles due to grain boundary damage. Others react with residual moisture during handling. Engineers are addressing these issues through surface coatings and improved encapsulation methods. Early demonstrations show that protective layers of aluminum oxide can prevent moisture penetration while maintaining flexibility. Continued refinement will determine how many times materials can realistically be reused without degradation. Even partial recyclability represents a major advance over current systems that often end up as hazardous waste. The broader implication of recyclable solid-state batteries is a complete change in how energy storage fits into society. Instead of a linear chain of extraction, manufacturing, usage, and disposal, the cycle becomes regenerative. Cities could operate local collection centers that return used cells to nearby refabrication plants. Power grids could manage energy storage as a rotating asset pool, constantly refreshed with reclaimed materials. In this model, each megawatt-hour of capacity remains within the system indefinitely, turning energy storage into a sustainable infrastructure rather than a consumable product. Future innovation will likely combine solid-state chemistry with other recycling-compatible technologies. Hybrid batteries that use both solid and semi-solid components may simplify disassembly. Additive manufacturing could print new layers directly from recycled powders without full remelting. Artificial intelligence will guide material selection, predicting which combinations yield the highest conductivity and recyclability. As the field matures, these developments will merge into standardized platforms where all components are tagged, recovered, and reused automatically. The concept of waste will fade as every part of the energy system becomes renewable by design. By 2026, we are likely to see the first commercial electric vehicles using solid-state packs built entirely from recycled material. These vehicles will demonstrate not only technical performance, but also economic stability. The lessons learned will carry over to aviation, shipping, and stationary grid systems. Each success will reinforce the principle that technological progress includes responsibility for the materials it consumes. Closed-loop energy storage will stand as proof that efficiency does not end when the battery stops delivering power. It continues in the cycle that begins anew each time material is reclaimed. The transition toward recyclable solid-state batteries marks a defining phase in modern energy development. It connects chemistry, engineering, and policy into one coherent vision. The pursuit of higher density and safer power now merges with circular resource management. Each breakthrough brings us closer to energy independence built on renewal rather than depletion. As research continues and pilot plants grow into full-scale facilities, the promise of infinite reuse becomes real. Thank you very much for watching. Please like and subscribe.